All right, section 9.4 is titled Odds and Expected Value. There are two separate components to what we're going to do today. These are the two components. They're related ideas, but they're not directly affecting one another. So they will be two separate topics, really. All right, so we're going to start with odds. Odds are going to be described in terms of probabilities. So if P of A is the probability that an event A occurs, and P of A complement is the probability that event A does not occur, then the odds of event A are, we'll go O of A. I hate the letter 0, the letter O in this case, but we'll do O of A. The odds of event A are the probability that the event occurs, P of A, divided by the probability that the event A does not occur. It's also equally true that you can talk about counting the number of ways, like when you're thinking about like rolling a die, the number of ways that event A can occur, and then the number of ways that event A does not occur. This is an equal value. So these are the odds of an event A happening. And we'll do examples so you can see how they play into each other. This is the odds in favor of the event happening, and then we have the odds against the event happening, and all we have to do is to flip the fraction upside down. So the odds against A, so this is odds against, is the probability of the event not happening compared to the probability the event would happen, or the number of ways that the event would not happen compared to the number of ways that the event would happen. Now, please don't confuse what I'm saying here. I am not saying that these numerators are equal to each other and these denominators are equal to each other. That may or may not be the case. In fact, it can't be the case in general. Because probabilities are always numbers between 0 and 1, and the number of ways something can happen obviously needs to be a countable value, like 1, 2, 3, 4, and so forth. But it's the ratios that are the same, right? Fractions, reducing, things like that. All right, so let me show you how this actually works with an example, and then it'll start to come together. All right, we have a set of 8 marbles. 5 of them are red, and 3 of them are white. And we're going to choose one of them at random. Now, we've done problems like this before where we found, like, what's the probability of picking red, right? So what we do in that case is we compare the number of ways we select a red one compared to the number of total marbles there are, right? That's probability, is comparing something to the total number of outcomes, or the total chance compared to the chance of your event happening compared to the any chance of anything happening, okay? Odds does not compare those quantities. Odds compares the number of ways something happens to the number of ways it's going to fail to happen. Okay? So we're going to do the probability on part A that we choose a red. So what is the probability of choosing a red? Right, so there's 5 red, and there are 8 marbles total. So there's 5 out of 8 as the probability of selecting red. But then when we do odds of selecting red, we aren't comparing, so this is red compared to total. We're not comparing red to the total. What are we comparing red to? To white in this case, or to not red, yeah? So red was 5. The not red, or white, was 3. So this is a 5 to 3 ratio. Now, we've talked about this before in section 9.1. We talked, or not 9.1, it was in 7.4, I think it was, when we talked about proportions for the first time. Maybe even it was 6.4, whenever we encountered them the first time. What we looked at is we looked at a way of making a proportion or comparison of ratios. You can compare something a part to the whole or a part to part. Do you remember those phrases? When you compare a part to a whole, that's a probability. Or I should say a probability is comparing a part to a whole. Odds is comparing a part to a part. So if you'll remember, we had an example where somebody was saying that the ratio of boys to girls in a class was 5 to 6, and the person was surprised there was only 11 kids in the class. Well, that was an odds question. 5 to 6 was actually a question of odds. 5 compared to 6 instead of 5 compared to the whole class. So we have seen this idea before. Now, we can also work our way around this sort of backwards. That is, we can start out with something that's given in terms of probability and find the odds, or given in terms of odds and find the probability. Like the last example that we did, what we did is we actually were given the data itself and then find the information. So on example 2, we're told that the probability for rain for the day is 60%, and then we want the odds against it raining. Okay? So if the probability that it rains is 60%, that's 0.6, right? So what's the probability, the probability that it does not rain? 40%, right? Or 0.4. Okay, so this is the two things that we're going to compare. The probability it rains, the probability it doesn't rain. Now, this right here wants the odds against it raining, right? So these are the odds that it won't rain. That's what it's looking for. So we want the odds of no rain. So what would we do? Well, we're going to compare these probabilities. So we want the probability of no rain compared to what? The probability that it rains. So what's the probability of no rain? 0.4. And the probability that it rains is 0.6. And if we simplify this into a fraction in lowest form and so forth, what do we get? What is it? 2 over 3. Right, so the 0.4 of the 0.6, you can move the decimal on each of them to be 4 over 6 and then divide each by 2 to get 2 over 3. So the odds of it not raining, or the odds against it raining, is 2 to 3. Right, so for every 5 times that we guess, 2 times it's going to do one thing, 3 times it's going to do the other. That's sort of the idea behind what they're describing. Make sense? Excellent. Now, Theorem 9.8 actually tells you what we just kind of did, what I just did verbally, but in a formula kind of form. If we have the odds of event E and the odds are m to n, then the probability of event A is m over m plus n. So this is the likelihood or the number of ways that it happens, right? Our event happens. It occurs. And this is the event not happens. So when you're looking at these ratio over here, m is the number of ways that your event occurs, and m plus n, that's the way it occurs, plus the ways that it doesn't occur, that's the total number of ways any of these things would happen to begin with. So that's what you're seeing happen here. And then on this one, the odds against, that's the difference right here, is that it says against. We still have the m and the n defined in very much the same way. It's just that n is that it doesn't happen, and if it's against it happening, then we're saying it doesn't happen, so n's on top. And then the m plus n, the total number of ways that it's going to happen, is on bottom. And of course, as we reduce those things, we might actually end up having a reduced fraction that doesn't actually have the right numbers in the right places for what we actually just said because it's reduced. So let's do an example of how this works with a gender problem. We actually saw a gender problem very similar to this last class period. We're going to consider a 3-child family, and it wants to know the odds of having all of the same gender of kids. So the first thing we've got to figure out is all the combinations we can have of kids. One way to do that's a tree diagram, and since you guys are still intricately working in 9.2 on tree diagrams, I'm going to do this one with a tree diagram for us. We wouldn't necessarily have to do this one as a tree diagram, but it works for what we're doing anyway. All right, so child number 1 can be a boy or girl. Child number 2, boy or girl. Okay, that's child number 2. And then child number 3, also boy or girl. right, so looking at my tree diagram, what I'm comparing is the number of ways I get all the same gender to the number of ways I don't. So where on my tree diagram do you see all kids the same gender? Top branch, all boys, and bottom branch is all girls. So how many ways can I get all the same gender? 2. How many ways do I get different genders? 6. So this is odds of the same gender. So what we're looking at is we're looking at the number of ways that are the same gender compared to the number that are different genders. So the number you just told me that was the same gender was 2, different genders was 6, and if this reduces, it reduces to 1/3, right. So the odds are 1 to 3. So what would be the odds against having the same gender?
6 over 2.
Okay, 6 over 2 or 3 over 1. And we just write it as 3 over 1. We do need the denominator written, otherwise it's not a ratio. It doesn't have that the notation that makes sense in terms of the context. So I mean, I realize 3 divided by 1 is 3, but as a ratio, this is 3 to 1. Okay? So once you find one of these, you just flip it upside down. Yes, Shelley? The 6 came from the 6 places where we have different gender children. These are the 6 branches. I'm just circling the ending result. But they're the 6 branches where we ended up with boys and girls in our family and not just one gender of children. The other place that it can come from as a general statement, Shelby, is that if you know how many ways something can happen, this is 8. There's 8 ways that can happen. And you know 2 ways is it happening in this case, then the other one would have to be 6, which we wouldn't even have to count. We could just subtract to find that value too. So yeah, either way. All right, so this is odds. That's all that odds is it's a way of comparing a part to part. So we're done with odds now. Where have you seen odds before? There's a couple of different places that I can think of specifically where you hear about odds mentioned.
Like gambling and stuff?
Gambling, specifically you hear it mentioned with horse racing. I don't know why, but horse racing you always hear about odds, the odds of things happening. But you'll hear about it also with like casino gambling and things like that. The odds of winning are this to this. So your odds are better if your numerator's bigger, right, than the denominator. That's what you're really comparing. So, all right.
I have a question.
Yeah.
So when they say, like, in Hunger Games, may the odds be ever in your favor, like, they're saying, like, whatever is least possible.
In that case, they're saying least possible. That would be in your favor because you didn't want to go and be killed in a silly Hunger game, right? Yes. All right. The other thing in this section is called expected value. Expected value is a very practical concept, very, very practical. It's going to look a little bit funny when I write it down, but just bear with me and I'll explain what the pieces mean. It's really not a complicated formula. It's just a matter of being the only way to write this in a way that makes sense in general, okay? So we have an experiment, and the experiment has a bunch of possible outcomes. So they're actually writing the outcomes of the experiment as A's with little subscripts. A1, A2, A3, A4. You could write them as A, B, C, D, but they're writing with the subscripts because that actually lets us generally say we can go as far as we want. There's no ending point of a specific kind. And then each one of those events has a probability that they would occur. Okay, so if you're rolling the die, there'd be 6 events, and the probability of each of those events would be 1/6, right? If we were, flipping a coin a bunch of times, the same kind of thing. You know, the probability of each of the events happening has a 1/2 in that case. So the way that we calculate expected value, and we call it with capital E, is we take the event that happened times the probability that that event happened. And we do this for all of the events. So event 2 times the probability of event 2. All the way until we get to the very last event times the probability of the last event. So event happening, and all of these are numbers, okay? So I'm not talking about like boys and girls anymore. I'm talking about they have to be numerical values for it to be expected value to make sense here, okay? So these are numbers we're adding and multiplying together, obviously. I don't multiply boys and girls, so just to clarify. All right, a game is considered fair if the expected value is 0. Okay, So if you get an expected value out of your game of 0, then you have a fair game. We're going to see how that plays out with some of our casino examples in a moment. Here, we're going to first talk about a roulette wheel. Have you guys seen a roulette wheel before? It's just a spinner, has a bunch of numbers on it. It has the numbers 0, 0, 0, like 2 zeros, 1 0, and then the numbers 1 through 36. And one way to bet is to bet on a single number on the thing. So you spin it, you're betting that it's going to land on a 6 or whatever. Okay, that's one way to bet. There's other ways to bet on a roulette wheel. You can bet on colors because the wheel is also colored. You can bet on different aspects. But one way to bet is on a single number. Okay, so it'd be like rolling a die and betting that it's going to land on a 2. Okay. If the ball lands on your number, then you get 35 chips plus the chip that you played. So you give them one chip. Okay. If you don't land on your number, you lose your chip. If you land on your number, they give you your chip back and they give you 35 more chips. Do you have a picture of what visually is going on? Okay? So the first thing we want to talk about is what is the probability that the ball will land on 00?
38.
1 out of 38. And where'd you get 38, Rachel?
1 through 36 and then added 2 0.
Yeah. There's 38 possible outcomes. The numbers 1 through 36, the number 0, and the number 00. So the probability that you will land on 00 is actually 1 out of 38. Okay, everybody good so far? All right. This literally happens, not joking. My father-in-law, my in-laws are not like gamblers. Like, it's not a bad thing. They treat gambling like people treat arcades. They'll go and they'll go when they're in Vegas or whatever, and they'll play for an hour with a set amount of money, and they win, they lose, they whatever. It's spare chump change when they play. So they're not, selling the farm or something like that. So I don't want you to think badly of my in-laws for playing a roulette wheel. However, you might think badly of my father-in-law for the mathematics behind his reasoning. So we will look at that in here in a moment. When my father-in-law passes a roulette wheel, if he sees, there's a board, I should tell you this. There's a board beside roulette wheels that tell you what the last however many spins have been. So they tell you like the past history of the spinner for a certain number of spins, okay? So he passes the roulette wheel, he sees this board, and if the board has not landed on 00 in the history of the board, however many last spins it is, he'll put money down on the 00. All right, so if he bets one chip, and one chip is worth $10, the question is, what is the expected value of his bet? And more importantly, we're going to explain what that expected value means in context. Okay? So, according to the probability, or according to the expected value formula, we're going to try and figure out what the expected value is by taking the outcome, what happens, times the probability that it happens. Now, one probability is that you land on the 00, which means he wins money. And the other probability is that you don't land on 00 and he doesn't win any money. There's only two outcomes in this scenario. You guys with me? So I'm only going to have two things that are going to be multiplied and then added together. That's all I'm going to have. So basically I'm going to have one possibility is that he wins, and this is times the probability that he wins. And then I need to add that to, the probability or the likelihood that he loses, the amount that he loses, I should say it that way, times the likelihood that he loses, the probability here. All right, so let's kind of fill in what happens. Like, what happens when he wins? How much does he win? He wins 35 chips. Does he win 36 chips? No, because the one chip was his to start with, right? He really wins 35 chips. That's what he wins. And that's how much money in this scenario? $350, because it says that each chip's worth $10, right? So if he wins $350. How likely is he to win? 1 out of 38. That was part A. Okay, if he loses, what's the result of that? How much does he lose?
$10.
He loses $10. So since it's a loss, we're going to say it's negative 10. Okay? So this is basically like looking at the, in your wallet. When you look in your wallet before you played, compared to you look in your wallet after you played the game. One of two things happens. There's either 350 more or there's 10 less. You guys with me? This is the part that people get always tripped up on, is the value of what's happening. Probability then. What's the probability that he loses?
37.
Yes, indeed. 37 over 38. All right, so this is one of those cases where we're not working in fractions here. We're talking about money. So using the fractional component of what's going on here is really not all that helpful. Your calculator is quite helpful. So what I'd like for you to do is to enter this into your calculator, and I need a decimal approximation with 2 decimal points because this is money, right? And yes, it's going to be negative. Definitely going to be a negative value. That's perfectly fine. We'll talk about the context of what that means after this. All right, what'd you guys get? Negative 0.53. Okay, so 0.53, and this is money, so this is like 53 cents, right? So what does it mean? Well, it means something like this. On average, or if we played the game a whole bunch of times, that might even be a better way to start. If the game were played many times, then on average, sometimes we would probably win occasionally if we played the game enough times. Agreed? I mean, everybody gets lucky sometimes, right? I mean, we would probably at some point win, but most of the time we're going to lose, right? 37 out of 38. It's most of the time we are going to lose. So if the game is played many times, then on average, we would lose, that's why it's negative, $0.53 or 53 cents every time we played. Now, in reality, that's not what happens exactly, right? We don't. Every time we play, we either lose 10 or we gain 350. But on average, over the span of playing the game a whole bunch of times, on average, we would lose 53 cents for every time we played the game. That's why the casino has to win. I mean, right? They have to have this in their favor, otherwise they don't get to build the big building and have the waitress and, I mean, they can't do any of those things. It's a business. It is a business. That's the whole point. So on average, the house has to win more than the consumer has to win. The customer has to win. All right, so let's do another example. This is not worded very well, so I will fix that as we work it. In the television show Deal or No Deal, are you guys familiar with that? Okay. A contestant is down to 2 cases with equal probabilities of them being chosen. The cases have $250,000 and $1. If the game is fair, and I don't mean fair game like I just described it before, so I don't want you to think that that's what I mean. But I mean like it's, what we consider when we mean fair. Like if you get some, I get some. That's what we mean when we say fair, right? If the game is fair and you are the banker, what would you offer the contestant as a deal? Okay. About half, right? So what would we do to find the actual value? Well, we do an expected value. All right. So we're going to do an expected value. Our expected value is to figure out what would happen on average. I mean, that's what an expected value is. It's just averaging what the outcome would be. So one outcome is that we win $250,000. And how likely is that going to be to happen? 1 out of 2. There's 2 cases left, right? Plus, what's the other possible outcome? $1. All right, so if there's another possible outcome of $1, how likely is that to happen? 1/2.
And will those always equal 1, the probability?
Yes, they will. The probabilities will always equal 1. Summed together, which is what you meant, right? Yeah. All right, so add those, multiply those, and then add them together. And I know it's not the way that they would give you a value on the particular game show we're talking about, but humor me for the moment and tell me what the banker should give you for your case.
$125,000.50.
Yep. Okay, so they're using expected values when they do this game show. Of course, they're not going to offer $125,000.50, but they're going to benchmark this as their number, and they're going to offer you slightly less. I mean, that's what they're going to do, right? For real on the game show. They're going to say, oh, look, it's about half, like you guys were saying, $125,000. And they're going to say, okay, well, I'll offer you 110 or something like that, right? That's what they do. But this is the way that we would calculate it. It's an expected value. Okay, let's try another one. There's a cartoon at the beginning of your section of your book, on this section, that's a cartoon about a lottery, is what it's about. And it says that the odds against winning the lottery are 55 million to 1. So the first question I want you to think about is, using those numbers, using that context, what's the probability that you win the lottery? So the probability that you win is 1 compared to what?
55?
Yeah, the total chances, which would be what? 55 million and 1. So there's your 1. Okay, so this is a real common, you can be careful. This is, the number 55 is in millions, so don't go adding 1 million. I have a shirt for my children that says, let's see how it says it. 100, no, the one that I have is 5. I think it says 5 million. 5, it's an Ethiopian shirt, and there's 5 million orphans in Ethiopia, and it says 5 million orphans or something like that, and on the back it says -2. And it was a shirt that we bought as a fundraiser for a family who was adopting 2 kids, and it kind of fit at the point when we were bringing home one of our 2 children, and we already had Eli. And so my daughter looks at that and says, oh, so that means there's 3 million now. No, this is kind of what you were thinking when you first said it on accident, right? Is that we've got the word million, but that's like a unit, right? So it actually means like 5 with, the number of zeros behind it. So be careful on that. So why is it 55 million 1 on the bottom? What happened there? You have to add all the outcomes, right? So in this scenario right here, this is the number of people who lose, and this one's the number who win, correct? This is an odds to begin with. It gave me the odds, winning, losing, right? So when we're looking at, and I recognize that 1 divided by 55 million and 1 divided by 55 million 1 are very close values. But the principle is that we're including that in there as part of the number of people who've chosen to play the game, okay? All right, so let's take a look then at this particular example. If the grand prize is $13,567,290 and a ticket costs $1, is the game fair? So we're going to calculate an expected value. That's how we decide if a game is fair. All right, so the scenario is you go into the wherever and you buy the lottery ticket and you pay them $1, kind of like my father-in-law paying the $10 to play on the roulette wheel. And one of 2 things happens. You either win or you lose. Now, there's going to be in a couple examples, I think, in your homework where there's a third outcome. Like, if you win in this way, you win this much, and if you win in this way, you win this much, or you lose all of it, kind of things like that. So that's possible as well. So like if you roll a 1, you win $1. If you roll a 2, 3, or 4, you win $3. And if you roll a 5, 6, you win nothing. Something like that. So in this scenario, though, it's not like that. You either win and you get all the money, or you lose and you get none of it. So what is the probability? So we've got 2 options. The option of winning times the probability that we win, plus the option of losing times the probability that you lose. And those P's, of course, are different values. So maybe I should call them P1 and P2 like your book does. All right, so if you win, how much do you win? 13,567,000. What's next? 289. Why is it 89 and not 90? You paid $1 to play. Right? Again, remember, the idea is in my wallet, what's the difference? In my bank account, what's the difference? If I paid $1 to play, then part of that money that they just made me back was the money I paid to play. So I actually only earned back, quote unquote, I don't like the word earn there, but pretend for a moment, you earned back $1 less than what they actually gave you as the winnings. What's the probability that you win? Yeah, it's part A, right? 1 over the 55 million and 1, like this. All right, then, if you lose, what happens? You lose $1, so that's -1, right? Because you paid $1 to play. You're out $1 in your wallet. What's the probability that you lose? 55 million over 55 million 1, right? Are you guys with me? Okay, go ahead then and calculate what this is. I hear lots of clicking. What did we get?
-0.75.
That's right. Did everybody get -0.75? Everybody good? All right. So this means on average, if I had, bought a whole bunch of lottery tickets, on average I would lose 75 cents every time I played the game, right? I mean, that's what this says to us. Now, what does that mean? Is the game fair? No, it's not fair. What would it have to be fair? 0. My expected value would have to be 0 for the game to be fair. All right, we have one more slide, and it's a continuation of this problem, so keep this problem in your mind. As with many state lotteries, the proceeds are often said to benefit education. Have you guys ever heard that before? You will. Anytime they want to do something with gambling or with lotteries, things like that, they want to benefit education. The proceeds, under these conditions, if all the proceeds benefit education and 1 million tickets are sold, what is the expected value generated for education from the lottery sales? So on average, what we found out on Part B was that every ticket costs the consumer 75 cents, which means that it goes into the state's budget as 75 cents, right? On average. That's what Part B said. On average, each ticket generates 75 cents of revenue for the state. And if we sold 1 million tickets, what would we have to do to find out the total generated for the state? Multiply them, right. So we would take our 75 cents, and this is now a positive 75 because from the perspective of the state, it's income, right? Times the 1 million. So what would this actually give us? $750,000. Whoops, I left a 0 off. So we generate $750,000 of revenue. Okay, roughly. We rounded the 75, I think, Rachel, didn't you? You gave me 2 decimals, yeah. So roughly, anyway, this is what we're looking at, right? Pretty close. The reality is that that's not what really happened. That's the rough estimate and on average thing, right? The reality is one of 2 things happened when 1 million people played the game. Either 1 million people played and they all lost, or 1 million people played and someone won. At least one person won, right? So we're going to presume in the case of the way this is sort of set up that it's one person can win, only one person. All right, so what are the actual possibilities? So one possibility is that no one wins. So if no one wins, and they all paid $1 to play, and 1 million people played, how much money did the state make? $1 million, right? So this is my $1 for my ticket. This is the 1 million tickets that we sold. So this means that when no one wins, the state actually gets $1 million. And that's what really happens. No one wins, state gets $1 million. Second option is that someone wins. So we're going to say one person wins. In other words, there is a winner. Even if it's not one person, then they usually, what they have when more than one person wins is they split the jackpot. Have you heard that phrase before? When somebody wins the lottery, there were 6 people who won the lottery, and then they split the jackpot. So the jackpot's still the 13 million. So one person or someone wins. So if someone wins, what happens? Well, still 1 million people played, so $1 million came into the government, right? But then what did they have to do? They have to pay out the $13 million for the prize winner, right? So they brought in $1 million, and then they paid out to the winner or winners $13,567,290, right? That's how much they paid out. So what happened to the state budget? What happened? The state lost money to the tune of negative $12,567,290. Now, obviously, as a Christian institution, we would tell you do not gamble, right? But what I want you to see from this argument is that this argument of something benefiting someone with a lottery is a very strange argument to make. Because either you're arguing that you want it to benefit, which means you want everyone who plays to lose, because that's the only way that education in this scenario benefits, is everybody loses. So I created a game that makes everybody lose so that I can win money. Or I create a game where people win, in which case the beneficiary, in this case education, doesn't get any benefit. In fact, it actually ended up costing the state money instead. Are you with me? So these arguments that people make for things, they don't really tell the whole story, and you need to be really careful as you're listening to media promote different, and this isn't the only thing, but promote anything like that. Start thinking, reasoning critically about whether or not they're really showing you all sides of what they're trying to say is happening.